Hello everyone. Today we have a new project, and what we are doing here is setting up a basic linear optimization model using OR tools. The idea is to find the best way to produce tables, chairs and cabinets given a few constraints like how much wood we have, how many labor hours we can use and how much storage space we can afford. And at the top we are importing the required OR tools packages. These cover constraints, the solver itself, variables, and the objective function. Pretty much all we need to build and solve a linear problem. And then, inside the main method, the first thing we do is load the native libraries. This part is necessary for OR tools to run properly. Right after that, we create the solver object. Here you can see that we are using this zip solver here, which is one of the solvers OR tools supports. And we have added a quick check. If the solver can't be created, we just print an error and exit early. And let's talk about the decision variables. We define three variables: tables, chairs and cabinets, and these represent how many units of each product we are going to produce. The lower bounds are all zero. That means we can't produce negative quantities, and there is no upper limit, so we use positive infinity. Okay. Next up is the set of the constraints. You can see, starting with wood usage, we know that each table uses 30 square feet, each chair uses 5 and each cabinet uses 20. So we define a constraint that the total wood usage must be less than or equal to 400 square feet. And same approach for labor. Tables take 4 hours, chairs take 1, cabinets take 3, and we kept the total labor at 50 hours. Then comes storage. Tables use 50 cubic feet, chairs use 5, cabinets use 35, and the total available storage is 500 cubic feet. So again we put that into a constraint. And finally we add some minimum production requirements. So we are saying we need at least 2 tables, 8 chairs and 3 cabinets to be produced. Okay. That's done with 3 separate constraints, each making sure that the value of the corresponding variable doesn't drop below the minimum. And that's okay. Let's continue. Once the constraints are set, now we define what we are trying to optimize. So in this case, it is profit. So we assign a profit value to each product. Tables give us $250 each, chairs give us 80 and cabinets bring in 180. Those coefficients go straight into the objective function. Then we set the goal to maximization. Here you can see, and so we are telling the solver choose values for tables, chairs and cabinets that stay within all the constraints and give us the highest possible total profit. Now comes the solve step. We call the solve method and store the result. Then we check if the solver actually found an optimal solution. If it did, we print out what that solution looks like, how many tables, chairs and cabinets to produce, and what the total profit will be. And after that we also show how much of each resource we are using based on that solution. Okay. For wood, we calculate the total square footage by multiplying the number of each item by its wood requirement. 34 tables, 5 for chairs, and 24 cabinets. Same idea for labor hours and storage space. So if everything works as expected and we get a valid solution, we will see the full breakdown: production quantities, total profit, and how the resource limits were used. If the solver can't find a feasible solution that satisfies all the constraints, it will just print that no optimal solution was found, and that helps us quickly catch if we make the constraints too tight or set up the model incorrectly. And let's run it. Yield and okay. So after running the model, here is what we get from the solver. And first, it confirms that a solution was found, which means the constraints were satisfied and the solver reached an optimal result. The recommended production plan is to make 2 tables, 33 chairs, and 3 cabinets. That combination gives us the highest possible profit without exceeding the available resources. And if you look at the profit, it is exactly $3,680. That's what the objective function returned based on the number of items and their respective profit values. Then we have the resource usage summary. We used 285 square feet of wood out of the 400 available, so there is still a bit of margin left there. Labor on the other hand is fully used. We hit the 50-hour limit exactly. That tells us labor was the tightest constraint in this case. And for storage we used 370 cubic feet out of 500, so again some room to spare. And the process ends cleanly with exit code 0, which just means the program executed without errors. So overall, this solution balances the resource limits and gives us the most profitable production mix under those conditions. If you wanted to experiment further, we could try increasing labor capacity or adjusting the product profits to see how the plan changes.